It can of course happen that during the restart the system is crashing again, and then we restart again and the system is crashing again, and so on. This is not likely that this happens multiple times, but it can happen at least once or twice. It's not so unrealistic to assume if the system had some hiccups, the system can crash also the next minutes again. And what we don't want to have is a behavior like this. Let's say we had an operation in our database executed, which was adding 50 to variable A, to data record A. And of course, we know how we undo this by subtracting 50 from A. And now there are two issues in restart. First of all, when we are redoing the transactions and our system is crashing, we want to avoid that we're doing this adding of 50 multiple times, because that was not the intention of the application or user that was implementing or executing this action. So that means that we want to redo the operations only once and only once. For redo, we have already seen that this is quite simple, why this works, and we will say that in the next slide again. But for undo, it's a bit more complicated, but it's the same idea. Undo and redo should both be idempotent. Because when we are applying undo, and again undo, because our undo was crashing and we don't know if it was implemented or not, we want to of course avoid in this example that we're subtracting multiple times 50 from our data record A. So I said that this was already discussed why redo is idempotent, and in fact this was, or should be quite obvious why this is the case, because we have page log sequence numbers inside our pages in our database. So we can compare the log sequence number with this log sequence number inside the page, the so-called page log sequence number. And if the log sequence number in our log entry is strictly larger than the page log sequence number, then we know that we have to still execute this redo information, otherwise not. So it cannot happen that we are applying the same action multiple times because of these keeping track of the most recent page log sequence number that made a modification operation to our page in our database. Now for undo, this does not work right away. We have to introduce a new concept called compensation log records. For every undo operation, we're creating such a compensation log record, and these compensation log records are included to our log, and they're carrying also a log sequence number. And the log sequence number of this compensation log records is used as the normal log sequence numbers inside the pages that are modified. So basically, we have our page log sequence number updated also for the undo operations, and the log sequence number we are using is not the operation that we wanted to make undone, but the log sequence number of a newly created compensation log record, CLR. Let's see how this can look like in this little example. We have two transactions, T1 and T2. We see here that transaction, or is assumed that transaction 1 is a winner and T2 is a loser. So we need to undo the information or the modifications done to our database by transaction 2. And like for the normal or the described restart procedure, we will analyze first of all the log to see which are the winners and the losers, and then we are redoing all of the described log entries using the redo information inside them, and then we start from the back of the log and need to undo the loser transactions. And now what we do in order to make undo also idempotent, we are creating compensation log records for the actions that we want to make undone. And here we call them, for convenience, for readability, we call them 7', 4', and 2' to correspond to 7, 4, and 2, which are the actions we need to make undone, because these are the actions of transaction 2, which is the loser. Of course, if we would not call it 7' or 4', but we would have again increasing log sequence number like in the previous normal operation as well, for instance 8, 9, 10, and so on. And these log sequence numbers inside the compensation log records, they are used to update the page LSN of our database pages. And then we can, when the restart, the crash happens and we have to do again the undo, and we don't want to do it multiple times, but only once, we can now compare these log sequence numbers here with our page LSNs in our database to see if this action has already been applied or not. So here's a depiction of a log after the complete restart. Complete restart means that before we have created the log, it looked like this. Let me just remove that. So like this. And then we started and we found out in our analysis phase that transaction 1 was committed, transaction 2 not, so transaction 2 is a loser. And then in the undo, after we were redoing all of these actions, in the undo phase, then we additionally create these log entries, these compensation log records, to be more precise. How are we doing this? Well, we're going through the log from back to the front. And the first one we want to, of course, compensate is this one here with LSN 7. And we do this. And before we do this, according to our write-ahead logging principle, we always log first before we do the action. So we are creating an entry here, compensation log record with LSN 7 prime. And now, looking what the action was actually doing here, we were subtracting 100 from A. This is what our redo information says. And the undo information says we have to compensate this at 100. And now look what's happened here in our compensation log record. Here we have the undo information from the actual operation. And this part here, this A is A plus 100 in our compensation log record. This is called redo information. This is a bit surprising, maybe in the beginning, or confusing, let's say, but it should be pretty clear why this is done, because we need redo information for our compensation log records, because if we would crash now, here, and the restart, we would go from the beginning to redo all of these actions, and then we also would redo this action here. A is A plus 100. And why is this important? Well, this action, A is A plus 100, is like the undoing from this subtraction. And when we have our page now updated, we're using the 7 prime log sequence number in our page PA as the page LSN. So it cannot happen that we are doing this action, this redo action, this undo action multiple times. Okay, this was 7. And of course now we see that we're not done yet. We have to continue, because here we see that the next, or the previous log sequence number of transaction 2 is this one here, the log sequence number 4 corresponding to this entry. And then we're creating a compensation log record corresponding to the undo information here, and this undo information, it's this one here. And this undo information, of course, corresponds then to our redo information in our CLR with LSN 4 prime. And one more, because we are not done yet, also the beginner transaction is logged here to be undone, and then we have logged all of the undo information. And perhaps we have already executed them successfully, so in the sense of that the changes are written to disk. But it can of course happen that we are not doing this because of efficiency reasons. We would only do the changes in the buffer, and the system is crashing now without the undo changes being written to disk. Is this a problem? No, it's not a problem, because when the restart happens, we can just again go through that here, and in the redo phase we would execute or check if they have been executed these undo information inside the CLRs, or the redo information inside the CLRs, which correspond to the undo information of the original operations. CLRs have this specific syntax here in our case to illustrate that, or to distinguish this from normal entries. They have also a little bit different shape. They contain, first of all, and this is important, of course, also a log sequence number and the ID of the transaction, the corresponding page where they want to make a modification to, and the redo information. And this redo information, that's important to note, is coming from the undo information from the original log sequence number or the entry that was describing the original operation. We take this undo information and write it here to our redo information. Previous LSN corresponds, like for the normal log sequence numbers or for the normal entries, to the next or the previous operation from this transaction. And here we have, this is also new for CLRs, undo next LSN is a pointer to the next modification of this transaction that needs to be made undone. And this is again important to note that the redo instructions inside the CLRs corresponds to the undo instructions of the normal operations. We see here that we have redo information, but we don't have undo information. Why don't we require undo information? Well, the answer is hopefully pretty obvious. We don't require undos for undos because the undo has to happen because we want to eliminate these effects of loser transactions or transactions that we want to roll back to a certain save point. So we don't require undo information inside our compensation log records because compensations are not meant to be undone. Again, I said this already on this slide. We see only this in textual form. We have this log at the restart beginning. So we go through in the redo phase to see if all of these actions here have been applied. And when I say actions here, I mean the normal entries, 1 to 7, as well as the new entries, which are compensation log records. We do in the redo phase check if these have been really applied to our database. And we don't really differentiate between the normal log entries and the compensation log records. We can be sure that after the redo phase, all of these actions have been applied. Not necessarily on disk, but in our buffer, so we are sure that at this point in time, the pages we are accessing in our database are capturing the actions described in our log. In the undo phase now, when we go back the log from the beginning to the end, we will identify here that the transaction 2, which was a loser, has been already undone completely because the undo next LSN pointer of this entry here, as we can see, is null. And then we know that transaction 2 was fully reverted. We don't have to do any more undo operations. It can of course happen, and this is why we're discussing this idempotence, it can of course happen that we have only a partial log because when we did the undo of the operation with LSN 7 and we wrote down the log entry in our log file and then the system crashed. In redo, like before, we're going the log from the beginning to the end. And then we identify here, when we do the undo now, the undo phase, we see here that the 7 prime, we don't have to undo because it's a compensation log record. But we see here in the entry for the undo next LSN that the operation described here is the next one to be undone. And then we're creating a compensation log record. I mean, in this example, we would call that 4 prime, which contains the transaction 2. Page PC, we're getting this from here, right? And now as the redo information of this CLR, we're taking the undo information, which is C minus 100. And so on, right? And then when we did this, we continue looking at this previous LSN pointer to come to this very first operation of transaction 2, which was beginner of transaction, and then we create also a compensation log record that we call here in this example the one with LSN 2 prime and the information necessary. So now we see that the log is created in this way, step after step, and if it would crash again after the 2 log sequence number, or compensation log record with log sequence number 4 prime, would not be a problem, because the next time we are restarting, we would just redo all of this information and then continuing undoing the entry with log sequence number 2 here, and would create a new entry, a new compensation log record with LSN 2 prime. Now, interestingly, or importantly, this cannot only be applied when the crash happens and we want to undo the actions of loser transactions, but in the same way, we can also roll back transactions to a certain save point, or in case of abort, undo the changes or the entire changes made by the transactions. Here we're talking about a system that's important, about a system which is still running properly. There was no crash happen. And what we are discussing here is the rollback of individual transaction when the application or the user is saying abort or roll back to a certain save point. When this happens, we can use our log, or we need to use our log to see which operations the transaction was executing, and just go backwards, so travel back in the log and execute the undo operations described in the log for this transaction or for this set of transactions, not for the entire transactions. Here we're talking about a system which is operating as wanted, so there's no crash happening. It's a normal operation procedure. So in this example, we have a transaction which is executing commands 1, 2, 3, and 4, and then decides by application logic or user that we have to undo changes 4 and 3 because we have to find a save point, and now we are jumping to that save point. That means the database system needs to undo all of these changes between the current point in time and the definition of the save point. The application is not doing this, the database system is handling the job, which is very convenient. But let's see how we do this. Here's the log information that we maintain throughout the operation of the system. Again, the system is not crashing, everything is good. We have normal operations, so we would create for the actions performed by these transactions log entries. And of course, we are creating log entry corresponding to the action 1, 2, 3, and 4. And now we can travel back from this point in time when the command that we want to go back to a save point comes. We can go back the log and look at the operations we need to revert. And for the actions we are reverting, we're creating compensation log records. We are reverting action 4, which was logged in the LSN 4. And we're creating a compensation log record here again for convenience. For notation, we write 4 prime as the new log sequence number of our CLR. And then we go back here and we're looking at this log sequence number 3, the entry, and see what was the action and what is the required undo information. And we're creating a compensation log records for this as well. And now we have set back the state of our system for this transaction only, of course, to the point after the operation 2 was executed. And then we can continue executing new commands. And the procedure or the mechanism described earlier works here the same way. In case there is a crash happening in our system, we can see that we have compensation log records. Obviously, the transaction is a loser because it did not commit. So we have to now carefully do the redo and undo. And for the redo, it's clear that we are not executing a command multiple times because of the page log sequence number. And now we understand by the previous discussion that also for the undo operation here, which are not materialized in our database, there's also no risk that we're executing them multiple times. And why is this? Well, we created compensation log records that also contain log sequence number, and these log sequence number are also written in our information page LSN in our database. So it cannot happen that we're executing here undo or redo multiple times. This is achieving what we wanted, the idempotence. And this is what I already mentioned. So we have transaction, individual ones, the system is running as normal, there's no crash happening, but some transaction had the wish to be set back to a certain save point or being set back entirely. And the system is handling this in the same way as described. We're creating compensation log records and we're updating the page LSNs inside the pages in our database system to make sure that also when a crash happens during this rollback of individual transactions, that we do not execute undo operations multiple times. So it can happen that the crash happens during the abort or rollback, but this is not a problem. And it should be clear by now in the discussions why this is not a problem. If you're looking at literature, sometimes there's a little confusion, a bit ambiguous in how you're writing this. In the end, it's all the same, but you can implement, of course, or you can write down that if a transaction was successfully aborted, that this transaction is now a winner transaction. So basically, you can treat like a successful rollback as equivalent to a commit, because this transaction does not have to be undone. We have to only make sure that we go in the redo phase through all of the log entries for this transaction. But this is not really a loser transaction in the common sense as we have introduced this earlier. So you can write down a log entry rollback for such successful rollbacks. So they are not losers in the sense of the definition of losers and winners as discussed in the beginning of this chapter. On the other hand, it doesn't really matter if you're writing down this information, because you will see anyway for those that were successfully undone that the undo next LSN pointer is null. So perhaps you're saving a little bit of computation or I/O when you're doing this trick with the rollback, because in the analysis phase you would not identify those which are successfully rolled back. So you don't have to at all look at this entry here. But for the semantic, for the correctness of the recovery, this is all the same.